In this video, we're going to demonstrate some examples of computing the tangent plane to functions of two variables. Notice the ingredients we were provided. We have a formula with x and y's in it, and this defines our surface, and presumably a curved, complicated surface. And we're also given a point as a starting place, or the location where we're going to build our tangent plane. In terms of the syntax that we saw earlier, the coordinates here are what we call a and b, and the function here is going to lead us to our derivative calculations. In this particular case, we were given a third value, which would be called our c, or the function value at a and b. We can confirm that if we plug in x equals 1, y equals 2 into here, we end up with 3 times e to the 2 over 2, or 3 times e to the 1. So this is the height at the point x equals 1, y equals 2. As an aside, you will need to know the formula for the tangent plane, which again is not too bad to memorize because it has such nice structure. The z-values on the tangent plane are given by the height where we are at the point AB, plus a slope at the point AB times x minus a, plus the slope in the y direction, again evaluated at the point AB, times y minus b. And we just go down the list and ask, what do we have, or what do we need to compute? We have a and b identified, and we actually have the function value there done. That's 3e. The two missing ingredients are these x slopes and y slopes. So we're going to need the x derivative in general, and we have to go back to the function for that. Notice the only x is in the second term, or second factor. So if we differentiate, we're simply going to get a 1 for that term, that factor, and all the others stay around as constant multipliers with respect to x. If we do the same thing with y, it's a little more complicated. 3x is a multiplier of constants. If y is our variable, then we have the derivative of e to the y over 2, which is e to the y over 2 again, but then times the chain rule, we have a 1/2 popping out for that. Our next step is to evaluate that at the point 1, 2. Again, this isn't simply the x derivative, it's the x derivative at the location we're interested in. And here that gives us 3 times 1, we can just call it 3, times e to the y over 2, which is e to the 2 over 2, which is again 3e. The y derivative, we're going to use this formula. There'll be 3/2 times 1, and then e to the 2 over 2 as well. And so that'll be 3/2 e. And that's the main calculation we need to do. The last step is simply to put all of those values into our formula for the tangent plane. It's a set of z values defined by the point we're at, the height we're at to start with, 3e, plus the x direction slope of that surface, 3e again, x minus our reference point for x, which was 1, or a, and then 3/2 e with the y minus, what was our reference y point? It was a 2, so y minus 2. And that's it. This sequence is something we're going to see in several different examples. Find the x and y direction slopes, evaluate it at the point we're interested in, and then construct the tangent plane. Next, what we're going to do is use our answer to find an approximate value for f of 0.95, 2.03. And note that this is close to the reference point that we used, 1, 2, which was our AB point. In other words, it makes sense to use a linear approximation or a tangent plane approximation to the function if we take points nearby. So from our tangent plane, the f of 0.95 and 2.03 is going to be approximately equal to, going back a stage, this is the exact formula for the height of the tangent plane. What we're going to do is approximate this, or treat this as an approximation to the actual curved surface for a nearby point. So that's why we're going to swap out our equals for unequals. This is the exact tangent plane, and this is the curved surface that'll be nearby. If we do that, we simply sub in the values. Here we have our x is 0.95 and our y is 2.03. The ingredients we had from the last page, 3e plus 3e, there's our x, 3 halves e, and there's our y. So 3e, and then our x value, minus 1. Notice this is a difference of very close x values. And then 3 halves e, the y value, 2.03, minus 2. Again, notice this is a small change in y, and that's all the ingredients we need. Going to our calculator, we get a value that's approximately 7.869. And that tells us that the height on the surface, the curved surface, is approximately that value. Now in this case, we actually have the formula for the surface itself, and we can evaluate it as well. Again, it can be a bit of a challenge knowing why we build these approximations when we can just use the formula itself. There is a guiding idea behind this that gets used in further mathematical applications. So for now, it's simply to get acclimatized to the idea of taking a complicated function like this and being able to approximate it with a tangent plane, a linear function. However, it's reassuring at this stage to be able to get the exact value and just make sure that we're not leading ourselves too far astray. The exact value of this function is going to be 3 times our x value, which is 0.95, times e to the y, which is 2.03, over 2. That's our exact formula for the surface with the x and y values subbed in. And that value is 7.86, a little bit different on the third decimal, 7.864. And so that reassures us that the concept of the tangent plane, the idea that we have a surface, we pick a point, and we can draw a plane that's a good approximation to the shape of that surface using the x direction slope and the y direction slope. Those two planes and surface are going to be close to each other as long as we don't go too far away from the reference point that we started at. Let's continue our examples with this function here, a rational function in x and y. Here we're asked to change our question a little bit. We're asked to find the points on the graph where the tangent plane is parallel to the xy plane, i.e. a horizontal plane. Well, what do we mean by that? What we're trying to distinguish is if we imagine our surfaces doing something, if we pick a point on the side of a hill like this, that is not what we're looking for. However, if we pick a point at the top of the hill, that is going to be a perfectly horizontal tangent plane. Well, what does that lead us to wanting in the tangent plane formula? Well, our tangent plane is defined by z equals f of a and b, plus the x slope at a and b, x minus a, and we'll clean this up a little bit, plus the y slope at a and b, y minus b. Put that back, there we go. What we want is this particular outcome here and not this outcome over here. If that's the case, we need this to equal 0, and we need this to equal 0 as well. In other words, we need to find a and b so that both the x derivative at ab equals 0 and the y derivative, or the y slope of the surface, also equals 0 at that same point. Well, if we're going to accomplish that, we're going to need our slope calculations. Our x derivative going up to here, and noting that we can rewrite this as we should to safely differentiate it. We can express this as this formula here to the power of -1. Then we can use the chain rule and the power rule together to find the derivative. With that in mind, we take the derivative of the outside function first. we end up with a -1 multiplier, all the same ingredients inside, with a y squared, and to the power -2, multiplied by, because of the chain rule, the x derivative of the inside. That will be 2x minus 2. And similarly, the y derivative, we go back to the original function. The outside power is still -1. We get the same expression inside, all to the power of -2. And then we take the y derivative of the inside, either here or thinking of it here. The key thing is we simply get 2y as that inside derivative when we're taking the derivative with respect to y. All right. If we quickly rewrite these as more rational functions or rational looking functions, we end up with this form, noticing everything inside here is the same as before, but now it's to the squared power, and we want to set that equal to 0 because we want a point where the x derivative equals 0. Well, the wonderful thing about that is the denominator doesn't matter. The only thing that matters is the numerator. So 2x minus 2 has to equal 0, or x equals 1. If we repeat that same calculation using our y derivative, we'll have all the same terms here. The only difference is the 2y. Going back a page for a moment, that's the 2y that we had as a multiplier from the chain rule. And we are also going to set that equal to 0 and see what happens. Again, the denominator doesn't matter. We can multiply it up. Multiplying it by 0 wipes it out. What we have here is 2y equals 0, and that only occurs if y equals 0. And that's it. So what we have as a result here is that to have both the x derivative equal to 0 and the y derivative equal to 0, and we want that again because we want a perfectly horizontal tangent plane, then we have to have x equal to 1 and y equal to 0. Well, that occurs only at the point x equals 1, y equals 0. That is the only location which will have a horizontal tangent plane. Perfect. Now let's follow that up and think about what that might mean, especially given that we've seen occasions where setting derivatives equal to 0 in the past has been a fruitful idea. If we have a flat tangent plane, like so, it's possible that we might have a surface that is peaking right around there. But that's not the only example we can get. We might also have a surface that is bottoming out at that point. One of our questions going forward is going to be, are there any other possibilities for what a horizontal tangent plane might look like, or what the surface might look like near such a tangent plane? It turns out there's a very common third case that we're going to encounter later. But we can already see associations back to our ideas of optimization. Find the points on this function that are locally higher than all the other points. Oh, that'll be a point where the tangent plane is flat, or in this case here, find the point which is a local minimum for the function, which is lower than the rest of the surface. Again, that point will be distinguished by having a horizontal or a perfectly flat tangent plane.